This is a recast of the 6,300-word piece, Perceptron Neural Networks, PNN, from Schneepat AI. This article discusses perceptron neural networks, PNNs, their structure, operation, applications, advantages, limitations, and advancements in the field. PNNs are praised for their ability to approximate complex functions and solve classification problems efficiently, making them valuable in machine learning and artificial intelligence research. They have been applied in various fields such as pattern recognition, image processing, and anomaly detection. However, PNNs have limitations in handling nonlinear relationships, lack interpretability, and are sensitive to outliers. Despite these limitations, PNNs are making an impact and continue to be developed and improved. Let's listen in.
Today, we're diving into the world of artificial intelligence and exploring perceptron neural networks, or PNNs for short. PNNs have been gaining a lot of attention in recent years due to their ability to approximate complex functions and solve classification problems efficiently. These networks are inspired by the functioning of the human brain and aim to simulate the way neurons interact and process information.
That's right, Paul. PNNs are a type of artificial neural network that consists of interconnected nodes or perceptrons. These nodes work together to process and classify input data. They have input nodes that receive data and output nodes that generate an output based on the received information. The workings of a PNN involve multiplying the input values by corresponding weights, summing them up, and passing the sum through an activation function to produce the desired output.
PNNs are particularly known for their ability to classify inputs into distinct categories. They are widely used in pattern recognition, image processing, and data mining applications. Their power lies in their ability to learn from examples and make predictions based on patterns in data. This adaptability and performance improvement over time make PNNs highly valuable in machine learning and artificial intelligence.
Absolutely, Paul. PNNs excel at handling complex and high-dimensional data by efficiently separating different classes and producing accurate results. They have been applied in various fields such as image and speech recognition, natural language processing, and anomaly detection.
PNNs are also notable for their simplicity, efficiency, and scalability. Unlike traditional neural networks, PNNs do not require complex training algorithms or multiple layers of nodes. They employ a feed-forward architecture that enables them to learn and generalize from input-output patterns efficiently. This makes PNNs a promising approach for further advancements in machine learning and artificial intelligence research.
It's interesting to note the historical background of PNNs. The roots of PNNs can be traced back to the 1940s and 1950s when early pioneers like Warren McCulloch and Walter Pitts formulated the first mathematical model of a biological neuron. Frank Rosenblatt further expanded on this idea in the late 1950s by inventing the perceptron, a simple feed-forward neural network. The perceptron was designed to mimic the functioning of the human brain, with the ability to learn and make decisions based on input data.
That's right, Theo. Despite its limitations, the perceptron model laid the foundation for the future sophistication and advancements in neural networks. It established itself as a fundamental milestone in the field of artificial intelligence. Over the years, researchers have built upon Rosenblatt's work to enhance the perceptron's capabilities, leading to the development of advanced algorithms like the PNN.
The PNN algorithm itself originated from Frank Rosenblatt's work at Cornell University in the 1950s. The early perceptrons were single-layer neural networks with binary outputs based on weighted sums of inputs. Although limited in solving complex problems, these early perceptrons provided the foundation for further developments in neural networks.
Exactly, Theo. Researchers have since built upon Rosenblatt's work to develop more sophisticated algorithms like the PNN. These advanced algorithms allow for more complex and accurate pattern recognition and classification tasks.
It's fascinating to see how far we've come in the field of artificial intelligence thanks to pioneers like Rosenblatt and their groundbreaking work with artificial neural networks.
Definitely, Theo. PNNs are just the tip of the iceberg when it comes to the potential of artificial intelligence. With their ability to approximate complex functions and solve classification problems efficiently, PNNs are paving the way for advancements in machine learning and artificial intelligence research.
Absolutely, Paul. PNNs have already found application in various fields, and their potential is only growing. From pattern recognition to image processing and robotics, PNNs are making a significant impact.
Right, and it's interesting to note that the evolution of PNNs has been shaped by key contributors in the field. Frank Rosenblatt, an American psychologist and computer scientist, played a crucial role in the development of the Perceptron, a single-layer neural network that laid the foundation for PNNs. And Geoffrey Hinton, a British-Canadian cognitive psychologist and computer scientist, revolutionized the field of neural networks with his work on deep learning and backpropagation algorithms.
Indeed, Paul. These key contributors have pushed the boundaries of what is possible with PNN technology. Their innovative ideas have enabled PNNs to continuously evolve and adapt to new challenges. And as technology advances in various fields, the application of artificial intelligence becomes more prevalent, making PNNs even more valuable.
Absolutely, Theo. Now let's dive deeper into the structure and operation of PNNs. PNNs consist of input, hidden, and output layers similar to the neurons in the human brain. The input layer receives external inputs, which are then processed in the hidden layer. This layer uses an activation function to determine the pattern's significance and extracts features for classification. The outputs from the hidden layer are then passed to the output layer, where the final classification decision is made.
That's right, Paul. The weights of connections between neurons in a PNN are continuously adjusted through a learning algorithm, enabling self-learning and optimization. This means that PNNs can adapt and improve their performance over time. Understanding the intricacies of the structure and operation of PNNs is crucial for leveraging their potential in various domains.
Absolutely. And when it comes to the architecture of PNNs, there are four main layers: input layer, pattern layer, summation layer, and output layer. The input layer receives the inputs, which could be values of various features in a dataset. The pattern layer consists of derived prototype vectors, each representing a specific pattern or class of the inputs. The summation layer calculates the distance between the inputs and the prototype vectors using a suitable distance metric, such as Euclidean distance. And finally, the output layer assigns the inputs to the class with the smallest distance.
Right, Paul. This architecture is crucial for accurate and efficient pattern classification. By breaking down the classification process into these four layers, PNNs are able to effectively process data and make predictions. And speaking of predictions, let's talk about how PNNs actually process data and make predictions.
Sure, Theo. PNNs process data and make predictions using a two-step approach. First, the network computes the Euclidean distance between the input vector and each training vector stored in its memory. This helps the PNN identify the most similar instances from its training set. Then, a kernel function is applied to these similar instances, transforming them into probability estimates. These probabilities are normalized, summed, and further processed to obtain the final prediction.
That's right, Paul. This combination of distance computation, kernel function application, and probability manipulation allows PNNs to effectively process data and generate accurate predictions. It's a powerful approach that sets PNNs apart from other neural network models.
Absolutely, Theo. In fact, let's briefly touch upon the comparison between PNNs and other neural network models. PNNs have been compared to feed-forward neural networks, FNNs, and recurrent neural networks, RNNs. While FNNs share similarities in terms of architecture and use of neurons, PNNs have the advantage of their specific learning algorithm that allows them to adapt and update weights based on separate classes of data.
That's correct, Paul. And when it comes to RNNs, which have dynamic memory capabilities, PNNs are often considered a better choice for dealing with stationary input patterns due to their simpler structure and faster learning process. These comparisons highlight the unique capabilities and advantages of PNNs in various applications.
Definitely, Theo. PNNs offer a promising avenue for developing intelligent systems that can effectively handle complex tasks. From image and speech recognition to fraud detection and financial forecasting, PNNs have already made an impact and will continue to do so in the future.
Absolutely, Paul. It's an exciting time for artificial intelligence and machine learning, and PNNs are at the forefront of these advancements.
One of the major advantages of PNNs is their ability to handle complex patterns efficiently. They can process high-dimensional data and extract relevant features, making them suitable for tasks such as image recognition, speech analysis, and natural language processing.
That's right, Paul. PNNs have the ability to self-organize and adapt to new information, allowing them to learn and improve their performance over time. This adaptability makes them highly reliable in real-world applications where data may be corrupted or incomplete.
Another advantage of PNNs is their parallel processing capability. They can handle multiple inputs simultaneously, which leads to faster and more efficient computations. This parallel processing capability is a significant advantage, especially when dealing with large datasets.
Absolutely, Paul. The high accuracy and efficiency of PNNs make them ideal for classification tasks. PNNs excel at classifying new input data accurately, thanks to their supervised learning approach. The network is trained by adjusting the connections between neurons based on the input data, enabling it to classify new data effectively.
And let's not forget about the robustness of PNNs to noise and outliers in data. Noise refers to random errors or variations in the input data, while outliers are data points that deviate significantly from the rest of the dataset. PNNs can handle these issues effectively by adjusting the weights and biases during the training phase.
That's right, Paul. PNNs are designed to minimize the impact of noise and outliers, making them robust models for data analysis and prediction tasks. This robustness is crucial in real-world scenarios where datasets are often noisy or contain outliers.
Another advantage of PNNs is their ability to handle large and complex datasets. PNNs excel at processing vast amounts of data, allowing them to tackle problems of topological nature. They can efficiently recognize and generalize intricate patterns in high-dimensional datasets.
Absolutely, Paul. The flexible architecture of PNNs also allows for the incorporation of various techniques for data preprocessing, dimensionality reduction, and feature extraction. This flexibility further enhances their ability to handle large and complex datasets.
Now let's talk about the training process of PNNs. The training phase enables the network to adjust its weights and biases to learn and make accurate predictions. The goal is to minimize prediction errors through iterative adjustments of the network parameters.
One common approach in the training process is backpropagation. In backpropagation, the error is propagated from the output layer back to the input layer. This allows the network to update its weights based on the difference between the predicted output and the desired output.
Through repeated iterations, the network gradually learns to improve its predictions and achieve better accuracy. The training process is crucial in ensuring that the PNN can effectively learn from the provided data and generalize its knowledge to new inputs.
Absolutely, Paul. Now let's move on to discuss the limitations of PNNs. One primary constraint is their inability to handle complex or nonlinear relationships within the data. PNNs rely on linear separation, making them less effective for datasets that contain overlapping patterns or do not follow a straightforward linear trend.
That's right, Theo. The initial assumption of linear separability can be unrealistic in many real-world problems, limiting the applicability of PNNs. It's important to consider these limitations before implementing PNNs in complex real-world applications.
Additionally, PNNs are sensitive to outliers. Even a single outlier can significantly impact the accuracy of the model, undermining its reliability in practical scenarios. This sensitivity to outliers is another factor that needs to be considered when using PNNs.
That's true, Theo. While PNNs have proven useful in certain domains, it's important to be aware of their limitations. Understanding these limitations can help us make informed decisions about when and how to use PNNs in real-world applications.
Absolutely, Paul. It's important to weigh the pros and cons of any machine learning model, including PNNs. By understanding their advantages and limitations, we can make better decisions and achieve more accurate and reliable results.
One of the crucial limitations of PNNs is their sensitivity to feature scaling and normalization. The article explains that scaling and normalization techniques are necessary to bring all features within a similar range. This aids in the convergence of the Perceptron algorithm. If these techniques are not applied, we can see biased predictions and hindered learning process. Features with larger values dominate the learning process, leading to incorrect weight updates and disregarding the contributions of smaller valued features.
That's a great point, Paul. Failure to apply feature scaling and normalization can have significant implications for the performance of PNNs. It's important to ensure that all features are on a similar scale, so that no feature dominates the learning process. This helps in obtaining accurate predictions and optimizing the performance of PNNs.
Absolutely, Theo. Another major limitation of PNNs is their lack of interpretability due to their black box nature. PNNs are composed of multiple layers of interconnected artificial neurons, making it difficult to understand and interpret the complex relationships within the network. While these networks excel at solving complex problems and extracting patterns from vast amounts of data, they struggle to provide meaningful explanations for their decisions.
That's right, Paul. The lack of transparency in PNN models hampers their application in domains where interpretability is crucial, such as healthcare or legal decision-making processes. In these scenarios, it's important to have comprehensible and traceable decision-making systems, which PNNs might not be able to offer due to their black box nature.
Exactly, Theo. Moving on, another challenge with PNNs is the difficulty in training and optimizing these models. PNNs are composed of multiple layers of interconnected nodes, leading to a complex and time-consuming training process. Achieving the desired performance requires careful selection of activation functions, optimization algorithms, and model architectures. Additionally, finding the optimal set of hyperparameters can be challenging due to the vast search space.
That's a great point, Paul. Training and optimizing PNNs can indeed be a challenging task. Researchers often invest considerable effort in fine-tuning these models to obtain satisfactory results for various applications. The lack of universal guidelines and the need for extensive experimentation contribute to the difficulty in training and optimizing PNNs.
Absolutely, Theo. Now let's talk about one of the main limitations of PNNs, their inability to handle non-linearly separable problems. The article highlights that PNNs assume that the input data can be linearly divided into two classes, which restricts their applicability in real-world scenarios where data may not exhibit such linearity.
Right, Paul. This limitation can lead to poor performance and inaccurate classification outcomes when dealing with complex datasets. To overcome this flaw, researchers have developed more advanced neural network architectures, such as multi-layer perceptrons, MLPs. These models incorporate hidden layers that introduce nonlinearity, enabling them to learn complex patterns and make accurate predictions in a broader range of applications.
That's an excellent point, Theo. While PNNs have their limitations, they still find diverse applications in various fields. For example, in pattern recognition and image classification, PNNs are powerful tools that can classify images based on their learned representations. They excel at tasks such as facial recognition, object detection, and medical imaging analysis.
Absolutely, Paul. PNNs have also found applications in bioinformatics for predicting protein folding patterns or analyzing DNA sequences. In finance, they can assist with credit scoring or stock market prediction. And in robotics, PNNs can be employed for tasks like obstacle avoidance or motion planning. These are just a few examples that showcase the potential of PNNs in contributing to advancements across numerous disciplines.
That's a great summary, Theo. It's important to recognize both the limitations and applications of PNNs. By understanding their strengths and weaknesses, we can make informed decisions about when and how to use them in real-world scenarios.
Absolutely, Paul. Being aware of the limitations of PNNs allows us to explore alternative models like MLPs when dealing with nonlinearly separable problems. And at the same time, recognizing their applications helps us utilize PNNs effectively and harness their potential in various domains.
One of the main applications of PNNs is in fraud detection and credit risk assessment. PNNs have the ability to analyze complex patterns and anomalies in financial transactions, allowing for the timely identification of fraudulent activities. They can also accurately assess credit risk by analyzing factors such as income levels, credit history, and socio-demographic data.
That's right, Paul. PNNs are able to efficiently process large amounts of data, providing enhanced predictive capabilities and minimizing false positives and negatives in identifying potential fraud and credit risk. This integration of PNN into fraud detection and credit risk assessment significantly improves overall risk management strategies for financial institutions.
Another application of PNNs is in the field of medical diagnosis and disease prediction. By analyzing patient data, such as medical records, imaging scans, and genetic information, PNNs can assist healthcare professionals in making accurate diagnoses and predicting the likelihood of certain diseases.
Absolutely, Paul. PNNs are particularly helpful in cases where complex patterns and interactions need to be identified across vast amounts of data. What's interesting is that PNNs have the capability to continuously learn and update their predictions based on new patient data, allowing for the refinement and improvement of diagnostic accuracy over time.
That's a fascinating aspect of PNNs, Theo. This technology represents a promising tool in the advancement of personalized medicine and could potentially revolutionize disease detection and treatment.
Definitely, Paul. PNNs are able to perform pattern recognition tasks due to their structure and functionality, which is inspired by the human brain. They consist of an input layer, a hidden layer, and an output layer, with each neuron processing information and transmitting it to the next layer.
Right, Theo. Through training and adjusting the weighted connections, PNNs can improve their accuracy and reliability over time. This makes them effective in tasks such as image recognition, document categorization, and data mining.
And in recent years, there have been significant advancements in PNNs. For example, the incorporation of convolutional layers into the PNN architecture allows for better feature extraction and classification accuracy in computer vision tasks.
That's a great point, Theo. Researchers have also explored the integration of recurrent layers in PNNs, which enables the network to effectively model temporal dependencies and handle sequential data like speech and natural language processing.
Absolutely, Paul. Another breakthrough has been the introduction of attention mechanisms in PNNs, enhancing the network's ability to focus on relevant features and improving overall performance. These advancements have expanded the applicability of PNNs in various domains, driving further research and development in the field.
And finally, the integration of PNNs with deep learning techniques holds great promise. By incorporating PNNs as an additional layer within deep neural networks, researchers aim to leverage the strengths of both models to tackle complex problems.
That's right, Paul. The combination of PNN's pattern recognition and classification abilities with deep learning's feature extraction capabilities can potentially result in improved accuracy and efficiency in various domains.
Exactly, Theo. This merger of PNNs with deep learning techniques offers a promising direction for future research in the field of machine learning.
And let's not forget about the use of PNNs in natural language processing tasks. They have proven to be effective in tasks such as sentiment analysis, text classification, and parts of speech tagging.
Absolutely, Theo. PNNs are able to capture complex relationships and patterns within textual data, making them valuable tools in tackling the challenges of language processing.
That's right, Paul. By training on large data sets and optimizing their weights through iterative processes, PNNs can accurately predict sentiment, categorize text into different classes, and identify grammatical elements.
Their use in NLP tasks has not only enhanced the success rate of these tasks, but has also contributed to the advancement of language understanding algorithms and models.
And that wraps up our discussion on the main points of the article. PNNs have proven to be advantageous in various fields, from fraud detection and credit risk assessment to medical diagnosis and natural language processing.
Indeed, PNNs have shown remarkable success in these domains by effectively learning and generalizing from input-output pairs. Their ability to separate classes with linear decision boundaries makes them particularly suitable for classification tasks.
Absolutely. PNNs are able to model an agent's behavior and reinforcement learning problems, allowing them to learn and maximize their reward over time. This is achieved through the backpropagation algorithm, which iteratively adjusts the weights of the network to improve its predictions and decision-making abilities.
That's right. And it's worth noting that while PNNs have been widely used for pattern recognition, image classification, and prediction tasks, they do have limitations. Their performance heavily relies on the quality and quantity of training data, as well as the choice of activation functions and network architecture.
That's a great point. PNNs can struggle with complex and non-linear problems, which limits their applicability in certain scenarios. However, Ongoing research and advancements in the field continue to enhance the capabilities of PNNs, making them a valuable tool in various real-world applications.
Absolutely. Looking ahead, future directions for PNN involve expanding their application to domains such as image recognition, natural language processing, and financial prediction. Efforts should also be directed towards enhancing the capabilities of PNN in handling large-scale datasets, improving generalization performance, and increasing robustness against adversarial attacks.
And while there are definitely challenges to overcome, such as training data scarcity and interpretability issues, researchers are actively exploring potential advancements and improvements in PNN. This includes developing more efficient training algorithms, improving generalization capabilities, integrating PNNs with other machine learning techniques like deep learning, and enhancing interpretability.
Ethical considerations and potential biases also need to be addressed when it comes to implementing PNN algorithms. Ensuring transparency and fairness in decision-making processes is crucial to avoid perpetuating biases or discriminating against certain groups. Additionally, the lack of interpretability in PNNs may hinder understanding and accountability, making it difficult to detect and mitigate biased outcomes.
Absolutely. Overcoming limitations and addressing challenges in PNN research is crucial to enhancing the effectiveness and applicability of this neural network model. Techniques such as feature selection and dimensionality reduction can be employed to process high-dimensional data, while optimization algorithms like stochastic gradient descent can address slow convergence and difficulty in finding optimal solutions. Future research should also focus on developing methods to improve interpretability and expand the scope of PNNs for solving real-world problems effectively.
And let's not forget that despite the advancements in deep learning models, PNNs remain foundational in understanding the basics of neural networks. They serve as a stepping stone towards more sophisticated algorithms and continue to inspire new approaches and algorithms in the field.
Absolutely. PNNs have been instrumental in advancing the field of artificial intelligence and have paved the way for more sophisticated models that can tackle intricate problems. Their simplicity and effectiveness should not be underestimated.
I couldn't agree more. In conclusion, PNNs have proven to be a valuable tool in various domains, but there is still room for further research and exploration. Efforts should be made to enhance efficiency and accuracy, explore applications in complex domains like natural language processing and image recognition, and adapt them to real-time and dynamic problems.
That's right. The future implications of PNN for machine learning are highly promising. Advances in PNN architecture and its ability to handle complex and nonlinear data open up new possibilities in fields such as image recognition, natural language processing, and autonomous driving. However, challenges such as interpretability and robustness against adversarial attacks need to be addressed through further research.
And that wraps up our discussion on the main points of the article. PNNs have proven to be advantageous in various fields, from fraud detection and credit risk assessment to medical diagnosis and natural language processing. Their potential for further research and exploration is vast, and we look forward to seeing how they continue to advance the field of artificial intelligence.